All right, today we're going to dive deep, and I mean literally deep, right into the Atlantic Ocean. We're going to pull back the curtain on these massive hidden rivers of water that are always on the move just under the surface. And believe it or not, they're shaping the climate of our entire world. So let's get right into it.
So have you ever actually wondered about that? You look at a map and the ocean just looks like this giant, still, blue thing. But it's not still at all. It's in constant, powerful motion. The real question is, what's actually making it move? What are the forces behind these invisible rivers? Let's figure it out.
Okay, so to really get a handle on this, we've got to zoom out and look at the big picture first. And that brings us to our first piece of the puzzle, the Atlantic's giant gyre. We're about to uncover this huge, swirling pattern that pretty much defines the whole ocean.
So, what in the world is a gyre? You're going to hear that word a lot, so it's super important. A gyre is basically a huge system of circulating ocean currents. The best way to picture it? Think of a giant, really slow-moving loop, kind of like a whirlpool that's big enough to cover an entire ocean basin.
Now, here's a really crucial piece of the puzzle, the direction it's all moving. In the northern Atlantic, this huge gyre spins in a massive clockwise loop. And trust me, that direction is absolutely not random. There's a reason for it, and we're going to get to it.
And this loop isn't just one big swirl of the same water. It's more like a giant two-part system. You've got these warm currents, which are basically rivers of heat flowing from the warm equator up towards the colder poles. And then you have the cold currents, which complete that circuit, bringing all that cool water from the poles right back down towards the equator. It's a perfect exchange.
Okay, to make this a little more real, let's put some names to these currents. A really famous warm current, that's the North Atlantic Drift. It's the one that carries all that warmth up towards Europe. And for a cold one, you've got the Labrador Current, which, as you might guess, flows down from the Arctic right along the coast of Canada.
All right, so we've seen the pattern, we know what's happening, but why is it happening? What's the engine behind all this? That brings us to the forces working right on the surface. We're asking a simple question. What gets all this water moving in the first place?
And the first big driver is actually pretty simple. It's something we're all familiar with, the wind. Yep, just the wind. But not just any breeze. We're talking about the huge, relentless, prevailing winds that are constantly blowing across the globe. They're the ones that give the ocean its first big push.
So how does wind actually move that much water? It all comes down to a simple transfer of energy. Think about it. As those powerful winds blow constantly over the ocean, there's friction, right? The air literally grabs onto the surface of the water, and all that energy gets transferred, dragging the top layer along with it. And boom, just like that, you've created a current.
But wait, the wind is pushing the water, but it can't just go in a straight line forever, can it? Nope, because it eventually runs into something big. That's our second surface factor, land. The continents. You can literally think of North and South America as being giant walls in a bathtub. They're just in the way. And here's the key part. These continental walls don't just stop the water dead in its tracks. They divert it. When that moving water hits a landmass like North America, it has to go somewhere, right? It's forced to turn. And that turn, that's what creates those giant looping gyres we were just talking about. It's the walls that make the whirlpool. Okay, but here's the thing. Wind and land. That's just what's happening on the surface. That's only half the story. To really understand the whole picture, we have to go deeper. And that's where we find the invisible forces at play, things like density, and even the spin of the Earth itself. Now this is where things get really cool. Deep down, the currents aren't really driven by wind. They're driven by density. So what makes water denser? It's a combo of two things, how cold it is and how salty it is. And the rule is simple. Colder, saltier water is way denser and heavier than warm, less salty water. And this density difference creates this incredible process. You can call it the Great Ocean Sink. Here's how it works. Way up near the poles, the ocean water gets super cold and really salty from ice forming. That makes it incredibly dense, so it just sinks. It plunges all the way down to the ocean floor. And from there, this deep, cold water starts creeping along the bottom, back towards the equator, pushing the warmer surface water out of the way and up towards the poles.
All right, there's one last force we need to talk about, and this one's a little bit of a mind-bender. It's called the Coriolis effect. Now, it's not a force like a push or a pull. It's an effect that happens simply because the Earth is spinning. The best analogy is trying to draw a straight line on a spinning turntable. Your line would end up curved, right? Well, that's what happens to ocean currents. The Earth's rotation deflects them from a straight path. So what does this have to do with our Atlantic gyre? Well, here's the magic. In the northern hemisphere, the Coriolis effect always deflects moving things, like our currents, to the right. And it's that constant, gentle nudge to the right that helps steer the whole system into that massive clockwise spin we talked about at the very beginning. See? It all connects. So we've seen the pattern, we've looked at the forces: wind, walls, density, spin. But now we get to the really big question. Who cares? Why does any of this matter? Well, that brings us to the most important part: how this whole system basically acts as a global climate engine.
So let's just do a quick recap of the four big players here. First, you've got the prevailing winds, which give the whole thing its initial push. Then you've got the continents, the land masses, acting as the walls. Down deep, you have the density differences creating the sink. And finally, the Earth's rotation gives us the Coriolis effect, which provides the spin.
And when you put all of that together, the push, the walls, the sink, and the spin, what do you get? You get a gigantic global conveyor belt. And its main job, its whole purpose, is to move incredible amounts of heat from the tropics up towards the poles. It's one of the planet's most important ways of balancing its own temperature.
So this incredible, complex system is one of the absolute key regulators of our planet's climate. Which leaves us with a pretty big and pretty critical question to chew on. What happens if this ancient, powerful system starts to change? That's a question with huge implications for every single one of us.